we would like to discuss about the either exam or our last lecture, which was about components, RTL component, combinational component. So please let us know. We can also have a look at reflections to see what did you write in reflection. Okay, any questions?
Yes.
Okay, please.
Can we solve the problem about hazards and timing?
The exam problem?
Yes.
You want to see the real, the right solution.
Here in the class.
Okay, we could do that. Could do that. Any questions? Okay. So before going to the reflections, why not to have a look at the hazard question? Where do I have the question? I guess I do have it here. Let me bring the question. Yeah, this is the midterm. This is the midterm, okay. And the question for the hazard is this. Download, open. Okay, so this is the circuit. Okay, this is the circuit, and we would like to draw the timing diagram for that. So this is the timing diagram. I put it here. Sounds good? Okay. Good? Yeah? So, the question was to find the timing diagram of this circuit, okay? And as you could see, it has been started with B0, C0, and A0, yes? Yeah, I guess so, okay. So, C at the beginning of 0, so C naught would become 1. This is 1 and A is 0, so the OR would be 1. X is 0 and 0 or 0 would be 0, and 0 and 1 is 0. So this is F at the beginning. So let's write the timing. So at the beginning, C prime, C bar is 1. Y is 1, and X is 0. X is 0, and F is 0. So this is at the beginning. But at some point, we change C to 1. When C changed to 1, C becomes 1. When C becomes 1, C bar would become what? 0 after 4 nanoseconds. So C bar would become 0 after 4 nanoseconds. So C bar is here after 4 nanoseconds, let's say this is 4 nanoseconds, it becomes 0. Okay. And before that, it was 1. So it was 1 up to here. After 4 nanoseconds, C bar becomes 0. Then Y, okay, now look at this gate. It is an OR. It has 0 and 0, so the output would be 0. But after 6 nanoseconds of the input, which became 0, so Y after 6 nanoseconds of this time. So this is this one. At this time, the C bar becomes 0. So after 6 nanoseconds of that, so this becomes 0. So Y here becomes 0. Okay. You see this? Let me put some with, let's say, this. This place 1 point at time. This is another section. This is the other one. And you could see that this is, yes, this is 4 nanoseconds, and this is 6 nanoseconds. Yes, please. For Y.
It should be 10 after 10 or 6?
10 after this position, yeah. So you see here, 4 nanoseconds after this, and 6 nanoseconds after that. So the Y is 10 nanoseconds after the transition of C. 10 nanoseconds. But 6 nanoseconds after C bar becomes 0, because it has a delay of 0. Now let's have a look at X. X is 0. It doesn't, okay, no. Oh, yes. No. C is 1 now. Yes, it should become 1 now. So blue. So C, this is become 1. So 1 and 0 become 1 here. So X becomes 1 after 6 nanoseconds of C becomes 1. So where C becomes 1? Here. Here C becomes 1. After 6 nanoseconds, X becomes 1. So X is 0. This is 4 nanoseconds. 6 nanoseconds is here. And before that, it was 0. So X is 0 up to here. And then it becomes 1 at this position. Now, X is 0, Y is 1. Oh, okay. So before Y getting 1, Y is 1 here. Then it, I didn't put it in the blue. So blue, Y becomes 0, 0, Y becomes 0, and 0, 0, this becomes 0, but with a delay. So Y becomes 0 after 6 nanoseconds of C bar getting 0. So C bar is getting 0 here. After 6 nanoseconds, Y, oh, what did I do? Oh, I already draw it. Okay. So Y becomes 0. So Y is 0, X is 0, so F is 0 for sure. But the point is this area. Okay. If you look at here, at some point X is 1, and also Y is 1. This is the hazard. At some point, both of x and y are 1. So at this time, what is the delay? 6. 6 nanosecond after this time, when both of them gets 1, 6 nanosecond after that, f becomes 1. So let's put 1. Okay. So f becomes 1 6 nanosecond after that, which is some place here. So it becomes 1. But later, y becomes 0 here, and after 6 nanosecond, f becomes 0 again. So 6 nanosecond after this, 6 nanosecond after this, y becomes 0 again. So this is the timing diagram. So maybe I erase the black one. So okay. Yeah, this is the hazard. We expected that f is always 0, but at some point, because of the difference in the path delay of these two, at some point y stays 1, and that causes f becomes 1 here.
The glitch is 4 or 6? 4, yeah?
What?
The glitch is 4
4 nanosecond, yeah. Okay? Any questions? Okay, good. If you agree, let's read some of your reflections. So the first reflection was RTL. Oldest thread, okay. The first one was Carol. Carol, is he here? Carol? No, Carol? Justin was here, yeah. Justin. How was the exam, Justin? Good? You get the 80 at least. 80. Very good. So RTL, what is the question? The question is, what is RTL? Then compare it with gate level and system level. Justin wrote that RTL is a functional level that is above the gate level and below the system level, electronic system level, in the computer architecture hierarchy. RTL employs registers which are connected with certain logic operations to create more abstracted functions than simple Boolean functions. RTL is used as it makes it much easier to optimize architecture and algorithm structure. Gate level is too fundamental to adequately optimize this complex and more abstracted aspect. We cannot optimize it. We cannot in terms of it becomes very large, very complicated. So we don't go for gate level when the circuit becomes large and larger and larger and larger. On the other hand, system level is even more abstracted and focuses on combining elements from the RTL. Very good. Perfect. So I guess it was good. Do we have Jonathan? Jonathan, okay. How was the exam, Jonathan? Good. Hope to get 80 minimum. RTL is a level of digital circuit abstraction that describes the flow of data between registers and the operations performed on that data. Very good. Gate level is a lower level that focuses on logic gates and their incantation in their interconnections, while system level is a higher level that models the overall. Very good. I guess that would be good for this. Let's go to the next reflection. What is component-based design? And give an example of a design where you use components. So let's go randomly down and select somebody. Okay, here. Samuel. Is Samuel here? Okay. Oh, Samuel. So with Justin. Okay. So it's good. The group, we selected the group. Samuel wrote, putting together many independent and pre-made parts, it's a component, it's a library, together to form a larger, more complex system. Very good. An example of this is our password project, very good, where we have an IC which acts as a 4 bits of SRAM using D flip-flops, an IC which compares our password together, very good. So you use these components, one for storing flip-flops, the other is comparing. So you don't go to design these two elements in gate level. You just use these components and you build your circuit. That's a very good example. Usually in your projects, if you have selected the projects, you go for component-based design, RT level, and not going to gate level. You might need to do some kind of gate level realization, but mostly you use RTL. Okay, very good example, Samuel. So Ina is here. Okay, I read it right this time. Good, Ina, your name. So component-based design is a design that incorporates pre-design. Very good. The key word is pre-designed, a library of the components. Those would be the components of the component-based design. Is good for complicated. It reduces redundancy, which makes the design as whole look simpler. I don't know why redundancy, but it's good. For example, in lab 4, we made a circuit in part 1 and then used it as an adder. Okay. What did you made in part 1? In part 1, what did you make? What did you make? Because you said you built something in part 1 and then use it in the adder. What did you build? What was the part 1? The circuit of part 1. What was that? Okay. So you use it for a larger adder. Okay. So you had, for example, a 4-bit adder, and then you used it for 8-bit adder or a full adder with carry. Oh, okay. It was only for 1 bit, and then you used it for making a 4-bit adder. Very good. Perfect example. Okay, now let's continue our lecture. Any questions? Okay, I guess we reached this point. We talked about data path, controller, and then I told you that we are going to focus on data path right now. Later, when we go to the sequential part, we will also talk about controller. But now we focus on data path, the path that has data, add, and, or, these things. So now we go to decoder. I guess we talked about it last time, yeah? You asked a question about decoder, yeah? Do I remember? Multiplexer, so not decoder. So let's go to decoder now. And I started telling you what is decoder is. I remember that, yeah. Before to go for that, when we do component-based design, when we do that, so it means that we have already built a good component which can be used in our future design. So the component, the design of that component should be complete, should be perfect. We have thought about everything in that component in regards of timing, delay, gates, optimization, and so on. So usually when we build a component, we think about the functionality, so it should function as what we want. We think about how to implement that and optimize it, simplify the circuit. we should think about cascading. So because that would be a component which will be used to build bigger components. So if we want to use this component to make something bigger, we need to cascade them, put them together to build a larger component, a bigger component. So we should think about cascading. So that's something. We should think about configurability. How do we use this component to make something else? How to configure it? We should think about the application of this component. Where do we use this component? And also, if we had the time, we go to Verilog. So I will give you each component with gate level realization and also the Verilog description, which I don't think we touch this position here. If we had time at the end, we touch it, but not very truly. So this is something that for each component we try to do: function, implementation, cascading, configuration, application. The first thing that start is decoder. We talked about decoder last time. In decoder, we mean that you have a binary. You have a binary number, and this is some kind of coding of something which is the number. The number is 0, 1, 2, 3, but we coded it as like 0, 0, 0, 1, 1, 0, 1, 1. So when we want to decode it, we want to reach to that number. How do we reach that? How do we design? We design something called decoder. The decoder accepts 2-bit input, and has 4 outputs. The outputs represent the number. So if this output is set, it means that the number is 0. If this output is set, it means that the number that we have input is 1, and also 2 and 3. So this is the decoder, some kind of decoding the binary number and making 4 numbers out of it. So the things that we would like to have is something like that. This is the truth table. The first step of designing for a combinational circuit would be drawing the truth table. The truth table is this. When we have 0, 0, then we would like the output 0 to be 1, and the rest is 0. So it shows us, okay, your number is 0. If we have 0, 1, then we want number 1 to be 1, and the rest 0. When we have 1, 0, number 2 is 1, and the rest is 0. And when we have 1, 1, number 3 is 1. So the truth table is that. And it is very simple. If you look at each column, it is just a NAND, is an AND gate, a min term that we could use to build that circuit. So there are 4 outputs. Each output uses one AND with the min terms corresponding A0 or A0 not, and A1 or A1 not. So the circuit would be something like that, very simple. So here you see the first one would be A0 not, A1 not, the first min term. The second one would be A0, A1 not. The third one would be A0 not, A1, and the last one would be A0, A1. So very simple, because each output has only one 1. You don't need to draw the corner map. It has only one midterm, so you use it. Okay? Now let's look at this. This is the truth table that we built. It's very good. We've built a decoder. But usually, I have told you before that it is good if we use NAND. NAND is a better gate. I guess I showed you the gate, the transistor implementation of NAND. In NAND, we have 4 transistors, but in AND, we need, at the end, we need an inverter to invert our NAND to AND. Actually, we build NAND first, and then we invert it to get AND with transistor. And it has 6 transistors. AND has 6 transistors. NAND has 4 transistors. So it is better if we use NAND for our circuit. So why not use NAND? So why not using NAND? This. Is it okay? You might say, no, it is not okay. When A0 is 0 and A1 is 0, then I0 becomes 0 and the rest becomes 1. But I wanted it to be 1. That one, the I0 becomes 1 and the rest 0. So I will tell you what's the difference. We wanted to decode. So we decode like that. We decode that like this. So what's the difference? We decode like this. When A0, A1 is 0, then I0 will get 0, the rest gets 1. So it's some kind of decoding. You know that I0 is not active. And by active here, I mean 0. In our previous design, when I am saying that I0 becomes active, I meant 1. It becomes 1. But here, I am changing my notation. What difference does it make? It is just a notation. I am saying that, okay, I am building a decoder. When you put a binary number at that as the input, the corresponding output gets 0, and the rest would become 1, which means not active. So here, being active means being 0. Okay? Do you have any problem? This is something that we decided. So we use this notation. And it is better because it is using NAND now instead of AND. And NAND is a better design. So why not this? Yes?
So in the second example, if it doesn't output any, if it outputs 0, then you know that it's true.
0 means that this is active. So if for example, I2 is 0, the rest is 1, then you know that you have entered 2, the binary number 2. If I1 is 0 and the rest is 1, then it means that you have input 1. Okay? So it's something that we decide. This is our circuit, and it is actually very good because it uses NAND. It's better. So here, to show this, we put a circle at the output, and this circle tells us that the output gets 0 when we want it. The output is 0 when it is active, and the output is 1 when it is not active. So look at this symbol. So this symbol is showing that it is active low, not active high. If we didn't have this symbol like what we had before here, we don't have this circle. This circle is just a connection. We don't have that not circle. So this is active high, but this one is active low. So we call this, the first design was active high outputs. This design is active low outputs. Okay? Okay. Now let's think of something. We are going to design something that I could cascade it. For example, what do I mean by cascade? For example, I have a 2 to 4 decoder. This is a 2 to 4 decoder. 2 to 4 decoder. Later, I would like to build, as you had something in your lab, we want to build a 4, for example, to 16 decoder. 4 input, 16 outputs, 4 to 16 decoder. So my thinking is that I build something that I could use these to build that. This is my goal. I would like to reach a point that I design something that I could use it iteratively, repeatedly, to get a larger design. For doing that, we introduce the concept of enable. We would like to have some kind of enable for our design. The enable, as the name tells you, the enable is that when the enable is active, the system works. When the enable is not active, the system doesn't do anything. So this is the idea of enable. So let me just first use an enable, put an enable here, and then later I use it for cascading. Okay. So what to do? How do I build an enable? Do you have any suggestion? Enable. So, yes.
What's an enable again?
And?
An enable? What is it again?
I want something that when it is active, for example, it is 1, then this works. So it works as it should be. For example, if I put 0, 0 here, then this one gets 0 and the rest gets 1. But if I put enable as no active, disabled, so then it doesn't work. For example, here it doesn't work means that my output would be 1. All of them always would be 1. It doesn't get 0 at all. Because if all of them are 1, it means that decoder is not decoding. Decoder is not, all of them is 1. Okay? So what do we add to this circuit to, based on that, either get the previous output that we had or we get 1 always with 1 bit enable. Okay, it's really easy. If you AND this to this, let's say AND it to this, we put it in this AND. It's NAND, a 3-input NAND. So if enable is 1, then this NAND works as it before. It depends on the inputs and it outputs I1 and but if enable is 0, then this is NAND. So whenever the one input is 0, the output is NAND. NAND is 1. So if enable is 0, all of your outputs become 1 without looking at the inputs. The inputs, whatever it is, the output is 1. So it means that we disabled the circuit to work. Somehow it is not enabled. Everything is 1. And 1 it means that it is not active because it was active low. The 0 shows that which input was there. But if enable is 1, then the circuit works as it's before. Okay? Okay. Good? Okay? So let's see. We need enable for cascading. So we are adding a bit to our design. Before we had 2 inputs, A0 and A1 with 4 outputs. Now we have added another input called enable, and we want to build a circuit with enable which works like this. When enable is 1, the circuit works as it is before. So 1, 1, 1, 1 is as before. 0, 0, 0, 1, 1, 0, 1, 1, and you see that these are the active low outputs. But when enable is 0, we would like the circuit not working. So the output is 1. Okay? And this is done by this enable pin. Good?
So what would be the use of
What's the use?
Yeah.
We will see an application of that. But before that, the concept is this. when enable is active, the circuit works as before. But when enable is not active, is disabled, the circuit doesn't work as it was before. And for the decoder circuit, which does not working, the decoder means that the output is not active. It's 1 for everything. So this is the meaning of not working. So the decoder is not working. When enable is not active, the decoder doesn't work. It doesn't look at the your inputs. It's always output 1 to the output. Okay? Yes?
For the enable, on output, input 3 before 12, it would input of 1, and in the case for that to be on, the A0 and A1 also need to be 1. So
No.
3 or 1, it would input as 0 as well, right?
No. Yeah. You see, enable is 1. Okay? Okay. Enable is 1. And then you are saying that A0 and A1, both of them are 1. So when enable is 1, it means that the circuit is working as before. Before that, when A0 and A1, both of them were 1, what happened? What will happen? What will happen? This one gets 0. You see? Okay. Now, let's say enable is 1 and A0 is 0 and A1 is 1. So what should happen? So since enable is 1, then it means that it works. So what is its work? What does it do? So the input is 1, 0. So it means that this output should become active, should become 0. So again, I repeat, when enable is 1 here, I mean enable is active, then the circuit, the design works as it is before. And decodes. The circuit decodes. But when enable is 0, the decoder doesn't work. It doesn't decode. The output is 1. It means that it didn't decode. Okay? Follow me? Yeah? Questions? Okay. Now let's have another observation here. Remember that I told you that when we have a design, a component, then we build it, we package it, and we'll give it to the other people to use it. Okay? We have a package, we have a bag. I told you we have a bag. I will give you my bag. Okay, this is my bag. Look at the bag, and there is a decoder there. You could use it. Okay? And I told you, when we are building a component, we should think about the timings, the design, what will happen to the timing. So I will design, and I will tell you, for example, I design something that it has a 2-level, for example, circuit, and so 2-level circuit, this one has 4 nanosecond delay, this one has 6 nanosecond delay. So the delay of my design is 10 nanoseconds. Okay? So you expect that when you use the design and when there is something changing, a transition there, after 10 nanoseconds, the output changes. Okay? This is the timing. Good. And also, I told you the delay depends on what. If you remember, I wasn't emphasizing on that because it is not our course, it is the electrical design. It depends on the capacity and the resistance of the circuit, R and C, RC. Yeah? Does it make sense? I don't want to know what would be the equation for the delay value with the value of R and C. But I just want you to know that when R gets larger, the delay gets larger, gets more. We have more delay. If C gets larger, we have more delay. Okay? Capacitance and resistance, they are two factors that making delay in our circuit. The delay means that you change something from 0 to 1, then it takes time to the output to be appeared. And I showed you in the transistor that we have a channel, then if you change the voltage, then it takes time to electrons to reach that position to make something. So this time depends on the capacitance and resistance. That's it. No more electronic. Now go back to digital. So the capacitance is important for delay. Now, look carefully. When I put this here, and I am saying that this is one input of my design, and you could use it as a component in your design. So we have another design, and somebody is going to use our decoder. Our decoder has EN, A0, A1 as input and something as output. So in this design, somebody is trying to use my design, and it assumes that I have an input, and there is already an agreement between the designers, in the logic designer, that if you have an input, the capacitance of that input is a very specific amount. And it depends, the capacitance, it depends on the things that it can see in front of it. Now that the capacitance depends on that, and I want to build something that it has an equivalent capacitance as one connection, this circuit is not good for my component-based design. Why? Because if you look at this input, inside the circuit, this input goes to many places. And these many places make the capacitance of the design more and more, the resistance of the designs more and more. And it is not good for this design. This design is thinking that I am using a pin that has a specific amount of capacitance, not 4 times of the capacitance, the capacitance of the logic. So it is not good. And that in that design, I was assuming that I have this capacitance and I will get a delay of this, but I put it in my design and then I see, oh, the delay is much more, and it's not good. So what do designers do when they design components? They try to make an input as really an input, just goes to one gate, not more than that. So to do that, we do this. Look at it. Very simple. We put, because inverter, as I told you, is the best component in transistor. For inverter, we need 2 transistors, one PMOS, one NMOS. We put them together and we build an inverter. So inverter is almost free. It's very good component. It's very good element. So we put an inverter here. Now look at this circuit. The outside world sees an input, it looks at an input, and this input goes only one place, not 4 places. And output of this gate goes to 4 places. And output of this gate is inside my design. So here is my design. This is my design now. So I should think about the delay and how could I make it better, and I do something inside my component. So if, because this goes inside my design, not outside. The outside world now has a really good input. The one input which goes to only one gate, which is this one. And the delay of one gate is something specific and everybody knows, so they can use it for that. So when we build a component, we should be very careful about how to build it, how to design it. Something like that. Okay? Any questions? Sorry, just give me 1 minute. Didn't work. Are you thinking about it? So the outside world is happy now. So they know that my design only goes to, in my design, it only goes to one word. Okay, let's continue. Now, I put an inverter, yes.
I was just wondering why the NOT gate affects why it matters.
Because internally, I am getting the output of this inverter and use it in my design. Okay, so this is something internally. But outside world has an input which goes only to one gate, not more. Before that, it was like this. It was like this, where the input from outside world going to several gates, and it means that it will affect the delay of that circuit, their circuit. They use our design, and then they get more delay than expected. So it's not good. So what do? We put this. So now, if they use this design, the delay would be the delay based on one gate, not more. And so what happens inside? Something happens inside. Here inside, we used our inverter to reach to 4 gates. Okay? So it, no. Okay. I should give you the transistor level to understand exactly what happens. But here, since we have an inverter here, just to give you an idea, the inverter is something like that, if you remember. It was a PMOS and NMOS transistor, and this was the output. So this inverter, when we put this inverter, the input of this inverter is this, which goes to outside world. But inside, we have this output here, this is the output, which goes to our inside circuit. This output has much more current power than this one. So this one, if gets more current, the delay gets more. But this is a very good thing for making more current. So it is good. So the output of the inverter is good for 4 gates. We don't worry about the delay here. Okay. It's not, you don't know it well. I cannot explain more because we need to go to the transistor level and so on. Yes? Yes. So with this inverter that we added, our enable should be 0 if we want it to be active. So that's the change that we have done because of this design idea that we had. So now we have this. Our enable get invert inside. This circle means that our input is active low. When it is 0, it is enabled. and when it is 1, it is disabled. It is not active. Okay? This circuit means that, and this corresponds exactly to our circuit. In this circuit, when it is 1 input 1, everything would become disabled. So it becomes 0, so everything would be 1, 1, 1, 1. So it is disabled. But when the input of enable is 0, then everything is working as before, as a decoder. So now, because of this inverter, we have built an active low input, active low decode. So this inverter, the last truth table that I show you is this. When it is 0, then it works. When it is 1, then it is disabled and it doesn't work. The output is 1. And so here, again, you see active low enable with active low outputs. We started from something. We made 2 changes to that, and now we have active low enable with active low outputs. So this will give you an idea why you find a component and you see that it is active low input. Why? Why didn't they have it active high? The main reason is this. They put an inverter inside to make the design almost independent. The outside world doesn't change based on our design. Okay? So active low enable with active low outputs. Any questions? Now, if you be smart and look carefully, you could ask me the same question for this input. This is an input, and it comes from outside world, and it goes to different places, at least 2 places. So again, here we have an input which goes to more than 1 place, which is not good. I told you that this is not a good design, and outside world becomes would not be happy with that. They would complain about this. So what to do? The same thing. What do we do? Here for A1, I put 2 inverters now instead of 1. For my A1, this line, I get it from here. For my A0 node, I get it from here. So this, I don't put this, I put 2 inverters. So 2 inverters. For the gates that I want A0, so for A0 also, A0, I put 2 nodes. For the positions that I want A0, like here, I want A0. So I get it from here. For the places that I want A0 nodes, I get it from here. Okay? So that's again the same thing. So our design that really has 2 inverters for each input also for A1 and A0. 2 inverters. Okay, so we built a good component now, a good component with a specific delay which doesn't make other designs which doesn't increase the delay of the other design, only at the specific amount, and that's it. Now we use this for cascading. After we have done the functionality, we talked about delay, we tried to optimize it. Now we go for cascading. So what do we want to do? We would like to build a 4 to 16 decoder. 4 inputs, 16 outputs. So what do? We will use 2 to 4 decoder. So this would be our final design. Our final design would have inputs, would have a low enable, low active enable. It has 16 outputs, active low outputs. So this would be our final design, like what we talked about it in 2 to 4. This is the. So how do we build this decoder? Yes.
Would you use 4 2 to 4
Okay.
decoders in parallel?
Okay, that's it. So let's do this. So we have 4 2 to 4 decoders here. And of course, we have I0 to I15 as output. So this would become I0, I1, I2, I3. This one would be I4, I5, I6, I7, I8, I9, I10, I11, and I12, 13, 14, 15. Okay? So these are my outputs are there. That's very good. So what about inputs? We have 4 inputs. What do we put as input?
So like each
So we have 4 inputs, A0, A1, A2, A3. So what do we put there? And you know that when we have an input, only one of them should be active. The rest would be 1. Okay? So we have to build something like that. So what do we do? Okay. Here, the idea of enable comes that I told you that I need it for cascading. So we had an enable here for each of these decoders. Yeah, remember? We had enable. Somehow, when my input is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 1, 1, for these 4 numbers, I want this encoder to be active. Okay? Agree? And the rest would be disabled. And they don't give us any output. Their outputs are 1. Only this decoder will give us 1 output as 0 and the rest as 1. Yes?
So we could do set A3 as the enable to all.
Very good, very good. Not A3. You are reaching there. A3 and A2 also we need A2. Let's see. Okay. So somehow with this enable, when this is active, we just working on that. And we get the output of I0, I1, I2, I3. But when the number is 4 to 7, we would like this to be active. So this and the rest would be disabled. So this enable should be active at that time. And when the number is from 8 to 11, this should be active. And when the number is from 12 to 15, this one should be active. Okay? So let me see what did I say? I say from 0 to 4, the first one should be active. From 0 to 3. From 4 to 7, the next one. From 8 to 11, the next one, and from 12 to 15, the next one. So look at these numbers. 0 to 3. So let me write the numbers. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Then we have 0, 1 again. 0, 0, 0, 1, 0, 1, 0, 1, 1, and we have 0, 1 here. Then we have 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. And then we have 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay. So if you look at the first 4, what do you see? What do you see in the first 4? Yeah?
All of the 2 furthest left columns are 0.
Are 0. So A3 and A2 are 0 for this 4. What about this 4? A3 and A2 are 0, 1 for the next 4. What about this? They are 1, 0. And the last one, they are 1, 1. So it gives us the idea of that we could use A2 and A3 to select the one that we would like. Okay? So how do we select that? How do we use 2 input pins, 2 input bits, and select 1 out of 4? What? No. The component that we have. What do we have? We have decoder. Decoder does this. Actually, the AND is inside the decoder. You are right, but we moved from the gate level to component now. So you should tell us. You should propose decoder. Why AND? Why that? So you would like to select 1 out of 4 based on 2 inputs. This is decoder. Decoder has 2 inputs, 4 outputs. And based on the inputs, we select one of these 4. Okay? Did you get the idea? So we used 4 decoders first to make our 16 outputs. Then we thought that, okay, these decoders, they are not working at the same time, all of them. Each time, one of them is working. And the one that is working at one time is dependent of A2 and A3. So we have A2 and A3, and we would like to select one of the 4. So it is another decoder. Another decoder, 2 to 4 decoder, will make that. So let's see, what did we build? Okay, so this is our first 4 decoder. We put it, and we have now 16 outputs, and we use the input of A0 and A1 to all of them. Okay, because A0 and A1 selects which one do you want. Now we have to put another decoder to select that, and the decoder here, the output of that decoder. Look at here. The output of decoder goes to enable of this decoder. So whenever, for example, let's have an example. We have number 7. Let's say 7. 7 is 0, 1, 1, 1. This is 7. So when we have this input 0, 0, 1, 1, 1. When we have this input, we would like I7 become active. So now let's look at our design. We have A3 and A2 as 0, 1, and we have 1, 1 here. When we have 1, 1 here at the input for these 4 binary decoders, so it means that we are selecting this one, why it's not, so this, or that. When we put input 1, 1, assuming that the enable is active. So now we built something that selects between eyes. Now we have to activate only the one that we want, which is this one. We wanted I7. I7 is here. So if you look at A2, A3, they are 0, 1. 0, 1, this is a 2 to 4 decoder. 0, 1 makes which one active? Number 2. 0, 1 makes this one active, number 1, this one. So this becomes active. So let me put another color for that. So this becomes active. This is active, goes here. So if this active goes here, then it means that this is active now. And I7 gets 0. But if you look at the other outputs here, they are all inactive. So this is 1, this is 1, this is 1. So this is 1. So it means that the first decoder is not active. The second one was active. The third one again gets 1, so it is not active. And this one is not active. So if they are not active, it means that all of the outputs are 1. There is no output here. No output here. Only this one is active, and this one is producing I7 for us. So based on the input, we made two-level decoder. The first decoder, this one, selects between one of the 4 decoders that we have, and the second level decoders, which are 4 decoders here, they select based on the 2 least significant bits which output do we want. Okay? Look at the design. How beautiful is that? And also, we have an enable here, which we can also put it there. If this enable is not active, is inactive, then it means that all of the outputs are 1. And if all of the outputs are 1, they go to the enable of these 4, so the output of all of them are 1. So it means that we have built a global enable for our circuit. If this enable is 1, inactive, then all of the outputs get 1, disabled, inactive. But if this is 0, then this decoder is active. It works based on the A3 and A2, and it selects one of the decoders of this type. Good? Question? Somehow we could say that yes, they are at the first level. So this is the first level. So A3 and A2 reach here sooner, and then with them you get the output, and then if you get the output, then they become active. Again, say again, 0, 0, 0, 1, 1. Oh, okay. I've done that. I told you. Okay. No, 0. This 0, 1 is 0, 1. So it means that this is active. The number 2 is active. The number 1, sorry. This one would be active. 0, 1. So because this is. One what? A2 and A3. Okay, what's the question? I didn't get it.
Like 0, 1, 1, 1.
No.
Is 0 A0?
Yes. Yeah. No. 0 is 8. No, this is 0, 1, 1, 1 is the most significant bit is A3. And this, this is A2. Remember, the least significant bits goes to this level, because they want to select as the least significant. And the most significant bits select among them. So the select would be most significant, the least significant. So yes, A3 and A2, in my example, 0, 1 goes to them, and 1, 1 goes to A0 and A1. Okay? The application. So I told you I will also talk about the application of a decoder. Do you have anything in your mind? Have you heard in the lab? Did you use a decoder or anything anywhere else? Maybe in your project, in your future project? No? One application that I will show you is address decoding. Address decoding. What does it mean? You should read about this in ITI 1200, I guess, when we are going to interface to the microprocessor or micro. So when we would like to work with memory, it's good that I tell you right now. Let's say we have 8 kilobytes memory, 8 kilobytes. So the memory means that, so our group there, they are going to use a memory for storing their password, yeah? You are going to use a memory. And your memory, I guess, has only one location. You just need to store one value. But usually memory, for example, in your computer, you have memory of 1 gigabyte or 4 gigabytes. There are so many locations. So memory has several locations, and each location stores a value. For example, let's say this memory, which is, say, bytes, 8 kilobytes, it stores 1 byte at each location. And how many locations does it have? 8 kilo. 8 kilo location. It means 8 times 1024 locations. 8 kilo locations. Okay? So this memory has 8K locations. Each location could keep 8-bit number, 1 byte number. Okay? So how many address do we need for addressing each location of this memory? It is 8 kilo. How many bits do we need to address 8 kilo? I give you a hint. 1024 is 2 to the 10. So you tell me the rest. How many bits do we need for 8K? 10 bits is for 1024. We have 8. 3 plus, perfect, 13. This is 2 to the 3. This is 2 to the 13 bits. We need 13 address bits to address each location of the memory. Okay? So this memory that I gave you has 13 address. If you look at here, so it is, could I zoom? I don't know, how could I do that? Maybe I could do this. Let's try. Oh yeah, no. Could I? No, it doesn't have multi-touch. It is one touch. So I cannot do that. Maybe I can do this. Oh yeah, I can do that. So if you look at the memory has A0 to A12. It means 13 bits. A0 to A12. 13 bits of address we have for this memory. Okay? So that's the address. What about data? Each location has 8 bits. So we have also 10 bits of data here. 10 bits of data here. So we have, I didn't put it here, so it becomes more complicated. We have D0 to D7, and we have A0 to A12 as the address. Okay. Now, in my design, I want to have 64K of memory. 64K of memory, not 8K. But I have only 8K memories. So what should I do? I should use 8 of them. 8K memory becomes 64. Okay? 8 memory. Okay. So I will put 8 of these memories together. So there are 8 of them together. So when I have 64K memory, it means that how many address bits do I have? 16.4. 64K, again, 64K. K is 10 bits. 2 to the 10 is 10,024. 64 is how many bits? 2 to the 6. So it is 16 bits. So I need 16 bits to address 64K of memory. So I have A0 to A15 to address 64K memory. But my memory has 13 bit of address. What do I do? So this is the application of decoder. What do? I put A0 to A12 to each one of the memories. You see, A0 to A12 goes to the address of each memory. But I use A13, A14, and A15, the most significant bits of my address, to select one out of these 8 memories. You see, whenever you want to select something out of, if you have 3 inputs, selecting out of 8 components, we use decoder. So what I do, I am going to use a decoder, 3 to 8 decoder, and I will use A13, A14, A15 as the inputs of this decoder, and the output of decoder, each one of them goes to enable of each one of these memories. The enable here, we call it chip select, which I don't go to detail, but this is some kind of enable for this memory. So if the address is, let's say, 0, 1, 1, and 13 bits 0 here, so it means that I want my third memory to be active. This location is somewhere here. This address is from 0 to 8K. This is from 8K to 16K. This is from 16 to 24. This is from 24 to 32. This is from 32 to so on. So if I put an address like this, then these 3 selects which memory do I need. So the one 0, 1, 1 selects number 3, selects number 3. Number 3 is this. So this will be active. The rest would be inactive. And this memory will give me the location of what I want. Got it? This is an application of decoder for address decoding of memory. And it has been used a lot in the computer design. If you have a computer, not now, because now everything is put in one chip. But for my time, around 1989, 88, when XT, the computer XT came just recently, when I opened that, I did that, and I saw the decoder there. There was decoder to select among the memory, because at that time the memories were 8K and they wanted to build a 64K memory computer, so they used 8 of them and they used a 3 to 8 decoder, and I could see this IC. You look at this IC. What is the name of this IC? 14138. IC, 74. 74138 is a decoder IC. You could buy it, and it has 3 inputs as the inputs, 8 outputs, and 3 enables. It has 3 enables, not just 1 enable, because you could use it better. I don't go to details. Okay? That's it. So now what we covered, we just covered one component, decoder. We build it, we saw the functionality, we then thought about the delay, then we thought about cascadability, and we built it for cascadability. Okay, any questions? Thank you. See you on Tuesday. Yeah, have a good weekend.